Okay, very good. So, perfect. Thank you, everybody, for being here. And today is the first day of the fourth edition of High Performance Computing and Quantum Computing, CINECA and CNR IFN event that we organize every year, and for the fourth year, this one. And today I want to show you a little quickly the agenda for today. Today we will talk about we will have two different sessions. This year, this event will be in 2 different days, today and tomorrow. And today we will see in the morning the part with the quantum hardware and software providers, all the news in the field of the realization of new quantum hardwares and new software strictly related to quantum computing. And we will resume in the afternoon after lunch with a very interesting session regarding the relationship between quantum computing and HPC in all Europe. So we will listen to a lot of European supercomputing centers that will explain us their relationship with quantum computing, their vision of the relationships between quantum computing and HPC. So let me leave the floor to our director, Sanzio Bassini, that will introduce our workshop. Thanks a lot, Sanzio, for being here, and the floor is yours.
Thank you very much, Daniele. I'm Sanzio Bassini. I'm the director of the High Performance Computing Department that by definition says natural and physiological development process would include also the actions related to the quantum computing. I would like to thank very much Professor Apolloni and Professor Di Falco, together with Professor Prati, that would collaborate since a while with the preparation of this annual appointment. As Daniele said, this is the third year that the event took place. The last two, unfortunately, in video conference, in digital, and not in presence. We had hope since the very last minute to be able to organize the meeting in presence. That is not yet the time. That is, pushing us for working as much as possible, and the science would be the only real answers for facing the pandemic, that it would showing possible new waves of pandemic, which is a concern for all of us. I would like to thank Daniele and to Riccardo that it would organizing a very nice meeting, very dense. I would not taking too much time, but I would like to just remind or maybe share with all of you that in principle there will be a lot of potentiality with respect of further development processing. You are maybe all aware about the fact that the high performance computing simulations and quantum computing also will be part of the national centers that will be funded in the context of our plan for resiliencies, the national plan for resiliencies, funded by the Next Generation EU funds. That for us, it's a very important opportunity. We're talking about the investment, where the development process related to the sharing of experience in the cost of quantum computing will be one of the pillars of that such national plan. We're talking a very huge investment, and we're talking also about a very strong opportunity in terms of involving the scientific community, and also supporting the inclusions of hundreds of researchers, that it would represent the real asset, apart the development process related to the infrastructures, which would be one of the pillar of the plan. we are continue to working in the context of prestigiating the technology, but more important in familiarizing with the development process of quantum computing, mostly addressing what will be the development process for use cases and for the methodology that it would combine digital computation with the quantum computations. Indeed, the point related to the integrations of the two technologies will be one of the actions of the next coming years already, that it's in the strategic agenda of the Euro HPC, which is also one of our main drivers for sharing what will be the experience and the further opportunity. So that's for spending a few words for sharing with all of you a sort of scenarios related to what would be the next year's actions. We will continue to address the topics from this point of view, and I would like to conclude these introductions, very brief introductions. We are hiring a new component of our staff to increase the number of people that are be working for high-level support in the domain of quantum computing, for supporting the national and European community for addressing what could be the long way towards the exploitations of these very important technologies. Of course, there will be more and more staffing, and that it's, I think, one of the main point with respect of what could be the vision. So combining the development process of the infrastructures with the inclusions and increasing of the high-level support that will be, I think, one of the main tasks for CINECA. Thank you very much again for these days. It will be a couple of very dense days. The agenda is really very important, I want to say. I would wishing you a profitable meeting, and I'm enjoying the listening and the sharing the experience that you would put on the table with respect of this important domain. Thank you very much, Daniele. Thank you very much, Riccardo. Thanks you all. Professor Apolloni, very nice that you would open the sessions, and thank you very much to Professor De Falco also that it would sharing the introduction, just to contextualizing the meeting. I would remain in the back, and I would maybe sharing some opportunity for interactions. Thank you very much.
Thank you, Sanzio. Okay, so now I will leave the floor to the other organizer, Enrico Prati, that I thank for being here. And Enrico, the floor is yours. Thank you.
Hello, everybody. Good morning. Can you hear me?
Yes, we can.
Okay, so I'm sorry for a last-minute issue. It looks that my camera is not working this morning, but okay, it doesn't matter. I'm very honored for hosting today the two inventors of quantum annealing. So I think it was a perfect match today for opening our session to have some historical perspective of what happened at those days, let's say about 30, 40 years ago, when the idea came out. So let me just introduce this short session, which is a kind of different, which consists of interview of the two inventors, asking them some historical remarks. I think this is very useful for young people and students who just to create some connection with what has happened in the past and to better understand what is happening today with the invention of hardware of quantum computers. So welcome to the two professors. So I think I would like to ask to both of you, basically, who was working to the concept of quantum computing in the 80s, and how was the world at that time, the research world?
Okay, thank you. I did expect your question. So I went to a fast Google search about the 80s and review search on reviews of modern physics 2018. 80s, I find the following names. Benioff, 1980-1982, quantum Turing machine. Deutsch, 1989, essentially universally of the quantum circuit model. Feynman, 1980 and 1986. If I go to Abash Leader Review, I found 3 other papers. I cannot say who are the authors of these 3 papers, but Bruno, I think, is showing the reference there. So essentially, in 1988, Bruno and I knew the papers by Feynman, 82, 86. Did not understand the papers by Benioff and Deutsch because there was too much matrix algebra there, and we were not conversant with that. But Feynman paper was 82 paper was fantastic. It opened a whole quite new horizon. It was just a matter of order of magnitude argument. N quantum spins are able to solve a 2 to the n dimensional problem. Essentially, the solution of their equations of motion. Everyone who has tried to implement n spins as matrices on a classical computer finds that it ends working with 2 to the n dimensional matrices, and its computer very easily blows up. But Feynman said, well, you need not simulating the evolution of quantum spin system. You just let them run, and they will solve their equations of motion. This was the main input for our research. Then there was another paper by Feynman in 1986. In fact, the paper appeared in 1985, and I stole that from the Salerno library in 1985. Which was too hard for us at that moment. It was not just an order of magnitude argument, but it was a strictly technical proposal of a machine working with elementary components on its own, including the clocking mechanism. And in 1986, we are not able to answer to the main questions that Feynman posed. Will the clocking apparatus ever reach the end of the program? How long it will take? How do you manage such strange things as subroutine being in a superpositional state or being activated or not being activated? Everything was, how can your computation fill the possibility of taking another route in spite of the fact of that route not being necessary for that computation? It was too hard for us to understand. And in fact, mostly we went to that subject, the 86 paper by Feynman, just after our experience on quantum computing. We tried to understand the 82 papers by Feynman, and our main idea in our first paper was the talk to the Vieti school, was based on the following idea. The ground state is a perfect tool for searching for absolute minima of Boolean functions for 2 reasons. One that is obvious, it is an extended object. One which is for a computer scientist less obvious, because in the ground state there is motion. It's not sitting there in the minimum. It has 0-point oscillations, which mean that it can jump, it can tunnel between relative minimum. This was a dream for a computer scientist, says Bruno. This is what we implemented in the stochastic explosive application paper, in which we were working about quantum tunneling, and we did that by an unconventional approach, not the well-known Schrödinger approach to quantum mechanics, but via a non-standard approach, the stochastic mechanics approach by Edward Nelson, in which you can talk about trajectory and even picture that in your simulation. So in 88, the situation for us was explosive because of Feynman 1982 papers, and we were well aware that it would take. We had to be fast because the competition was coming on. So your question, how was the world at the time? My answer is very nice, thank you. We were young with a lot of ideas and a lot of freedom to exploit those ideas. Maybe Bruno can be more explicit about this issue. Bruno, that's your turn.
Yes, just to add some general remark on this point. Let's say that 80 was a sort of cultural revolution like 68 was for the young generations. Essentially, we moved from a symbolic infrastructure framing the scientific tool, scientific thought, were based on two-value logic and embedded programming. In essence, give me a well-formalized goal, give me axioms as environment conditions, and I feature for you the solution to a sub-symbolic environment where the starting point were data, and then I observe them. I look for a local compatible model, and I provide solutions accordingly. Just to remark to quote some points of some facts of that time, probability statistics start pervading the issues, both management and scientific issues in that time, starting to appear in the programs, courses, of both in computer science and in other fields. Then NP completeness issue, in the sense that computer science took by hand the limit of their capability of solving problems in a symbolic way because of the curves of the exponential growth of the time to solution. And so that was the time for the revival of neural networks. They was buried in the previous decades because not so general. They revived both because they was proven as a universal computing machine, but mainly because they was the template of a sub-symbolic approach to solution, giving place to the typical attitude of a human. It means experience, intuition, learning. The general idea is no matter why, provided it works. And so it states a new alliance between theory and practice. And simultaneous annealing was the template of the stochastic approach to optimization, where the optimization in turn was the clue of any sub-symbolic solution to problems. And as it is, it represented an alliance between physics and computer science. You feature a proper process, you fire it and wait for an equilibrium distribution that suggests the best solution to the problem. The only drawback was that you should wait. We don't know how long time to get the solution. Here, quantum physics appears as a dream, as a magic wand that, with the necessary caveats, should promise, not at time ensure anything but promise, the possibility of solving in one shot the path to the equilibrium of our stochastic process. At that time, we were not in presence of a quantum machine. That our problem was to simulate it in a conventional machine, getting results that proved to be suitable, having the tunnel effect as the atout of this quantum annealing approach.
Yeah, it's really fascinating to us. Also to hear that the discovery of the first ideas came at the same time where neural networks came out. It's an amazing connection, something deep. Okay. Let me ask another question. At that time, I think it was really difficult to understand which direction looked more promising. So you had some multiple choices. So some of them, maybe they failed, some did prove effective later. And also your idea proved effective. So how did you get the idea, and what happened?
In some sense, I already answered this question when I told you that in 1988, I did not understand Feynman's paper in 1986. It took me time until 2013 to understand something about Feynman's paper. So that for me was the necessary evolution of my curiosity about quantum computing. Maybe we can speak about that another time. But at that point in 1988, I had a personal tragedy. I was able to convince people of what Bruno says, that probability and statistics are central not only for mathematics and physics, but also for technology. I convinced the Italian Academy of this point and was punished. I got a chair in probability at Polytechnic School, which meant increase of salary, which was important, but meant also 950 students per year. So immediately after quantum annealing, my attention was drawn to teaching. I had to teach quite a lot for 3 years, but with the feeling that I had to teach not probability, but quantum probability. When I went back to the UNIME, which means Institute of Computer Science at University of Milano, I kept this idea. My students, Dario Tamascelli might be in the room, my students had to learn quantum probability to start with, understand Kolmogorian probability as a particular case of a more general theory of states on an algebra. Expectation is a concept prior to probability, which I did in my last days of teaching in Milano, which means I was drawn by quantum annealing to the idea that I had to teach quantum probability not to mathematicians or physicists, but to computer scientists, which was the subject of some experience in computer-aided teaching. Then I had to go back to the work of Feynman, and it's a fascinating machine. The clock is just a single spin excitation traveling as a spin wave along a line with some local deviations. Very elementary. No battery needed. The clock just works because it is on half a line. And being at the leftmost point of the half line, there is some kinetic effect, but by which it must expand to the right, following the program lines. By itself, which of course asks a question, will it reach the end? The answer is, it may be, it might reach the end without any battery. How long? Well, that's quite another question. But you can try this with many copies of the system and overcome this problem. But it is a very slow procedure. So Feynman himself had an idea which was clear, obvious. Plug in a battery to this quantum walk and let it push on the right. But every physicist in solid state and conceptual variable coming from that environment knows that if you put on a lattice a particle in a constant field, it moves a little bit away from the origin and then starts oscillating by block oscillations. So Feynman's idea, which looks very fantastic, you just plug in a battery or position-dependent magnetic field that it goes faster, did not work. Because essentially, if on a lattice, current does not flow unless you have some dissipation. And then back you are to the problem that this very fragile system can suffer from friction, dissipation, and so on. In this respect, we were able to, as far as computation was needed, as far as simulation was concerned, bypass the problem of a Monte Carlo simulation approximation of the ground state by Cosine equation, too long to speak here, and by the Imlander equation, too long to hear. But we were able to implement that and answer a question that a referee had asked already in 1988. How can you do without the complicated algorithm for simulating via Monte Carlo simulation the ground state? That's all.
Yeah, that's very interesting. Let me, so unfortunately, time is running very fast. We are going to start the first final remark by Professor Apolloni. So did you, just a yes or no answer, did you expect that the idea you have worked at that time will become something real in the hardware today?
That is your matter, sir, because you are working now in real quantum computers. I expect, but actually with the same let's say approach of supercomputers, in the sense that initially it was intended as the universal solution to problems. Then they work on a special application field where vectorizing the computation, etc., was possible and suitable. The same expect with quantum computing, where we can be able to solve the special classes of problems, nothing to do with the idea of having a mini quantum computer on our table.
Yeah, thank you so much. Thank you, both of you. It was really amazing time spent today with you to launch our event. We are so grateful that you accepted our invitation, and you also gave the perfect starting point for the next session and the next speaker, who is exactly going to talk about adiabatic quantum computing and quantum annealing. So let me leave the floor to the chairman of the next session, which is Riccardo Mengoni, and let's start with the event with the first session of today. Thank you so much, professors. Thank you so much.
Thank you for your invitation. Bye.
Thank you.
Thank you. Thank you, Enrico. Thank you, Professor Apolloni and the Falco, for this historical contribution. Very inspiring. So